Okay, let's get started. I'm Eric Bowman from Sandia National Labs. It's a great pleasure for me to introduce the first invited speaker, Professor Rob Bisseling. Rob is actually a joint invited speaker for both the SIAM parallel process meeting and the Combinatorial Scientific Computing workshop, which is still going on, actually overlaps with the meeting. It's still going on in the ballroom over there if you're interested. So Rob is a full professor in scientific computing at the Mathematics Institute at Utrecht University. Before this, he was a research scientist at Shell in Amsterdam. He got his bachelor's and master's degrees from University of Nijmegen and a PhD in theoretical chemistry from the Hebrew University of Jerusalem. He is author of the book Parallel Scientific Computing, a Structured Approach Using BSP, which is a very good book. I read it a couple of times myself, and he just finished the second edition, should be coming out this summer around June. He's also a co-author of the BSP-lib standard for bulk synchronous processing and has co-authored several software packages like Mondrian, SAW Doubler, and Bulk. So today he's going to talk about parallel tomographic reconstruction where combinatorics meets geometry. So please welcome Rob.
Thank you, Eric, for a nice introduction. I would like to thank the organizers of both the SIAM conference on parallel processing and the workshop on combinatorial scientific computing for inviting me. I really feel honored and honored to speak at the intersection of both, and I'll try to discuss a lot from the union of both. And I also would like to thank my PhD student, Jan-Willem Buurlager, who is here, and my former students, Timon Knege and Daniel Pelt, without whom this would not have been possible, all this work. Okay, so we'll start with an introduction to tomography. We'll finish also with tomography. That's the application that I will be talking about. And in between, we'll talk about combinatorics, sparse matrices. And we'll work from small to large, small problems which we can solve exactly, medium-sized problems where we can use heuristics, combinatorial heuristics, and large problems where we'll also add a little bit of geometry to get things done. Okay, so in the mathematics talk, you first set your notation, you fix the notation. So here, when I talk about Mondrian, it is the Mondrian with 2 A's. It's the software package that we have developed at Utrecht University over the past 18 years. And it's not the painter, but the painter is quite famous, Piet Mondriaan. He lived from 1872 to 1944. He lived in the Netherlands. Actually, he painted in my village, close to where I live, near Amsterdam. And he also lived in Paris and later in New York. So, an introduction to tomography. So tomography, there are many different forms of tomography, but what I will be talking about is where there is a source of X-rays and a detector, and you can think of a number of pixels, a detector containing maybe 1,000 by 1,000 pixels. And we're trying to find information about an object by seeing how much of the X-rays penetrate and how much gets absorbed. Now, one day a week I spent also at CWI in Amsterdam. It's a Center for Mathematics and Computer Science, and there they bought a CT scanner, and it's very flexible, and that way we can do all kinds of experiments. So what you see here to the left is this is the source of the X-rays. There you have the detector, and X-rays, they are being sent. And in between, there is a stand where you can put objects, and this is the object that we put in there, and it can rotate, and you can do all kinds of complicated trajectories and see what the effect is. So the object that we placed there is actually, it was a present by my wife Ronna on the occasion of the first edition of my book. It's modern art. It's from 2004. It's called Homage to the Style. The style is the art movement to which Mondriaan belonged. It's 100 years old, and it's transparent, which is nice because we can check what's going on inside. Usually, you use CT scanners to see things that are not transparent, for example, like the human body. And so this is 15 by 15 centimeters, and so we tried that. We put it in the scanner, and this is one projection of the art object. So other ways of doing tomography. This is called the helical cone beam. Human is inside, moves at a certain constant speed, and the scanner and the source and the detector rotate around it. So that is, and there are many different types of tomography. For example, a parallel beam, where you put the source very far away so that all rays are more or less parallel. Laminography, for example, if you want to see the layers in a painting. And then you probably are all familiar with tomosynthesis. It is being used in airport security screening. There's a limited angle where they look at what's inside your suitcase. Okay, so now what happens in tomography, we can translate this to a sparse matrix. And here what you see is we have four projections, and each projection is on a 5 by 5 detector, so 5 by 5 pixels, very small example problem. That gives rise to a matrix of size 100 by 125. Every row of the matrix represents a ray, an X-ray, and every column represents a voxel. So it doesn't matter that they are 3D, we just number them from 0 to 124, and then we look at what the effect is of this particular geometry on the measurements. So BI is the amount that gets deposited on the pixel, and the AIJ tells you whether a certain voxel is being hit by a ray. So ray I hits voxel J. So it could be 0 or 1, but if you take the length through that voxel into account, it could also be a different number. So this is a sparse matrix, but it's a very special sparse matrix because it is relatively dense. These rays, they hit from all sides. And so if you have a 5 by 5 by 5 object, then you could imagine that at least every ray hits 5 voxels, maybe more. So you get a sparse system. But nowadays we do have very high resolutions. So if you have a 4K by 4K by 4K voxel space, then you get 64 billion voxels. And in the sparse matrix, that would mean that you would have something like 256 times 10 to the power 12 non-zero. So this becomes pretty big, and so we get petabytes of data. And that means that actually small matrices we can store, but the really large matrices we cannot store anymore. And that means that we would use matrix-free methods. Okay, so now we start with the small matrices, and we look at what we can compute exactly. So in tomography, what you need to do is often multiply a sparse matrix and a vector. That's all these algorithms are based on that. And here we have the case of a parallel sparse matrix vector multiplication. And you see, in this case, we have two processors, blue and red. And all the data, both the matrix and the input and output vector, they are colored, meaning we have chosen a certain distribution. And then I like to show the input vector above the matrix, because you see this value of 2 is needed, because it needs to be multiplied by 4. It's needed by the red processor, and then it's added with the 1 times 1 into this 9. And you see, so if in a column there are two different colors, then we need communication. But also if you make a bad choice for the first component, I could have chosen red here, and then I would not need this communication. So in general, it is, we do need communication, and we do communication, computation, communication, computation. That's what we do. And then we can ask the question, we have all these partitioners that do a partitioning. What is an optimal partitioning? And we can solve that for small problems. And it will be easier if we just looked at bipartitioning, so splitting into 2. So what the aim of this work is to find optimal partitionings for matrices that are as large as possible. That was work with Daniel Pelt. And here you see, for example, an optimal partitioning for one of the smaller matrices from the Sweet Sparse collection, formerly the University of Florida Sparse Matrix Collection, by Tim Davis, who is also here. So this is a matrix with 15 non-zeros, and in this case, the communication volume is 3, because we have 2 rows that are split and 1 column that is split. Okay, so the aim is we want to color the non-zeros of the matrix, and we do want to have a good load balance, and that means that every processor should have a number of non-zeros. That's about the number of the whole matrix divided by 2, and to make it feasible, we round this up, if we have an odd number here, and we allow a little bit of slack. So we allow a load imbalance fraction of epsilon, because that gives more possibilities to reduce the communication. Okay, so then what is the method? It's based on branch and bound. This is actually also a picture by Piet Mondriaan. He didn't only paint abstract paintings, but this is the period before he went abstract. So the idea is that in this branch and bound algorithm, we can either assign, and we choose for every row or column of the matrix, either to completely paint it in a single color, red or blue, or we cut it. And that means there's a communication. So, and then in this branch and bound algorithm, we prune the whole tree, which has a size of 3 to the power m plus n, so it really explodes, by pruning based on the volume that we got, or the number of non-zeros. And I'll show a few of these bounds. So one bound we call a packing bound. Here we have taken the decision already to paint the first column red, the second one blue, and also the second row. You see that's the 0. The second row will be red. But that means that certain choices in the future become impossible. For example, assume that we want an exact equal number of non-zeros, 8 red, 8 blue. Then in that case, we already have 6 red ones, so we can only assign 2 more red ones. And then if you look at the second to last column, which has 4 non-zeros, then we cannot assign all of them to the red processor. So we have at least one cut, so an extra communication. So this is a packing bound. And another is between is another bound on the communication. And we get that by looking at the matrix as a bipartite graph. So in combinatorial scientific computing, we are used all the time to either use the language of matrices, linear algebra, or the language of graphs, and we move back and forth between them. So here you see that we've decided to have the last row to have it red, and the middle column to have it blue. That's the decision we've taken. And on the right, you see a graph. So the vertices to the left represent the rows, vertices to the right, they represent the columns, and there's an edge between a row and a column if there is a non-zero in the matrix at the corresponding place. So in this case, we see that we painted the row 2, we painted it red, meaning that the bottom row is red. Now, if we do not want to cut anything, it means that the first column, this one, should be completely red. But then also this row should be completely red, and so on. But I could also start with the blue one. And in the graph, it means that I follow a path going from row 2 to column 0 and continuing. At some point, I will hit the blue part. So it's inevitable that in this case, since there is a path from red to blue, that there will be a cut and there will be a communication. So the cut will be of column 2, because you see that this one, in this case, one edge is blue, one edge is red, and it means that we have a cut column. So here we have one path, but if we want to find multiple paths, they have to be vertex disjoint. We can translate this to a maximum flow problem, and that is being solved inside the partitioner called MP, very short name, Matrix Partitioner. It's on GitHub, so if you want to play around with it, you can try it. And this one managed to solve about a quarter of the matrices from the sweet sparse collection. Obviously, they must be the smaller matrices. Here we gave 24 hours to each matrix and see how fast it could solve it. And at the top you see that the new one, which is MP, the old one is MondriaanOpt, that they will solve, of all the matrices with less than 100,000 non-zeros, about 52%. And in the bottom you see that, well, the more time we give it, the more is being solved. And, well, one of the things we'll do in the future is obviously to let it run for longer times and to get even more matrices solved. Okay, so this is actually the smallest matrix that could not be solved within 24 hours. It's coincidentally, it's one we produced in Utrecht ourselves. It's called Cage 6. It is a 93 by 93 matrix, so it's really small, and 785 non-zeros. And you see 3 colors. They are mainly for artistic reasons. So there's the red and the blue. And the yellow ones are undecided, because if you're in a row with already red and blue non-zeros, and you're in a column with red and blue, it doesn't matter what your color is. So you can we use these, we call them free non-zeros, and we use these to improve the load balance. And often we get to perfect load balance just by using the yellow ones. Okay, now to the medium size problems. So there are heuristic partitioners, like often based on hypergraph partitioning. And here I want to present the medium grain method. A medium grain method is based on splitting the matrix A into 2 matrices, AR and AC. And we just put non-zeros either in one or in the other. Think with AC, think of those where you want to keep columns together. and AR where you want to keep rows together. This is what we want to do in partitioning, but you can't have it all. If we want both rows and columns all stay together, then we have to paint everything red, and we don't gain anything from parallelism. So we sometimes want the non-zeros to go with a row and sometimes with columns. And we want to give this freedom to the algorithm. And we do that really by putting one matrix, the AC, in the lower left corner, the other one in the upper right corner, but transposed, and then also put two identity matrices in the left upper and the lower right corner to connect them. And we'll see that in a minute. So how do we do that? How do we decide on AR and AC? Well, the idea here is do a simple split, count how many non-zeros there are in the row. Like the first row has 2 non-zeros. So when I take this one doesn't work very well, but if I take, okay, let's see if this, yeah, if I take that one. This non-zero is in a row with 2 non-zeros, but a column with 3. So it chooses to go with the row, and it ends up here. So for everybody, we take a decision, and you see, in this case, that non-zero takes the same decision. So this row stays together. That's this row. But sometimes, if you look at the second column, we have RRC, that column, they take different decisions. So that's why we have a non-zero here and 2 non-zeros here, and the diagonal connects between them. And this matrix B, we give to a one-dimensional partitioner. We paint the columns of this matrix either red or blue. And then we can go home again and fold back into this matrix where we started with, and we have a good partitioning. Okay, so now what we did was we started with a split, a partitioning, to create a partitioning. So it's a chicken or egg problem. What is first? So we needed a partitioning, and the only way we could do it was by having a simple partitioning. But then, in a case where it's chicken or egg, you can exploit that, because we can use the information after the partitioning to feed that back into the algorithm. And we call that iterative refinement, but it's not the iterative refinement that we know from numerics, from iterative linear system solving. It's combinatorial. So here you see the split of the matrix, which is the outcome of the partitioning. And we do the same thing. We say, okay, the red ones now become AR. It's arbitrary which of the two I choose. And the blue ones become AC. I feed it in. I get a different matrix B. And then that matrix B, I partition again, but it's a limited partitioning. It's a refinement. We only do an improvement. And for those of you who know about the partitioning methods, we do a Kernighan-Lin refinement. It's like local improvements. And that works very well. Here we see a matrix, a bit bigger matrix, where we got the optimal solution of 11 communications. And here I show a performance profile of a number of different methods, 6 methods, compared to the optimal. Because the aim here of having optimal solutions is that we can once and for all say how good are our partitioners, how good is medium grain, or fine grain, which is a method developed by Umit Chatal-Jurek and Cevdet Aykanat. So we have these 6 methods here, and what this picture means is you see on the x-axis how far from optimal you are. For example, if this 2 means that the total communication volume is twice that of what is the optimal solution computed by our MP solver. And you see that for the best methods, this will be about 95% will be solved within that factor. And that's for all the matrices that we managed to get an optimal solution, which is about 800 matrices. And so you see 6 methods here. The top 3, or the 3 those are using the Mondrian package. And the ones marked with Pato are also using the Mondrian package, but for the hypergraph partitioner, we plugged in the Pato package, so you can combine them. And what you do see here is that the fine-grained methods, it performs well. If you can add iterative refinement, and then you get up a bit higher. And the top is the Mondrian combined with Pato using medium grain. That's there you get very, very high. Higher is better. And if we want to give a single number to express this, then you see that the optimality ratio is the geometric mean of of the communication volume compared to the optimal, and then the lowest value that we achieve is 10% from optimal. So we're pretty close, and that's using Mondrian for the medium grain and the iterative refinement, but Pato for the hypergraph partitioner. Okay, so now if we go to larger problems, then we can use geometry to have an alternative way of dividing the voxel space. And the problem with high resolutions is that there are many, many voxels. So at some point, you may want to describe it differently. And here you see the red lines, they are possible cuts of, we're just thinking of splitting the space into 2 parts. So the red lines are potential places where we can split. And what happens is that if you take the middle one, the middle split, then many of the rays they are in black, either dashed or dotted, or the straight line also. If with the middle choice, then only one ray gets split, the one that goes from the bottom to the top, but the others stay within their part of the space. So that would be a good split. In 3D, of course, we use a plane. So the idea here is to find a good splitting plane based on load balance, because we do want both parts to have about the same amount of work. This is based on density of lines, and also reduce the amount of communication. And we try all 3 directions and choose the best splitting plane. And what is nice is that there is a theorem, like we have for sparse matrices, that if you look at the total communication volume V of the split, then it is the same as the split for P parts, the same as the volume for P minus 1 parts, plus the last split that you did. So that means that we can greedily just split it to 2. We don't have to worry about the current context decisions that we've taken already. This doesn't mean that if you do it optimally every split, that then the final result is optimal. You could have, we don't have the foresight in such a greedy procedure. Okay, so now we can compare the geometric and the combinatorial solution, because for small and medium size, we can express this as a matrix as well. So to the left, you see the first column that gives the communication volume for slab partitioning. It's just splitting into slabs, and that is current practice in parallel tomographic reconstruction. Next to it is our geometric method, and you see that we have about 2.5 million data words being communicated for this particular problem. And if you do it in a combinatorial way, so translating to a sparse matrix and then partitioning it, in this case for 64 processors on the bottom line, you get, if you partition by rows, you get about 4 million words. If you do it by columns, meaning you assign the voxels to particular processors, you get less, you get 35% less. So using Mondrian on the associated sparse matrix tells us that it is better to partition the columns than the rows. And what you also see is that if we would use two-dimensional methods where the matrix, where all the non-zeros are individually assigned to processors, we could get another 15% reduction in communication volume. This is using Mondrian itself. If we would use Pato together with Mondrian, we could probably still get a little bit better than that. But it would be impractical because for the large problems, we cannot even store the matrix. And so we settle for a one-dimensional column distribution in terms of the matrix. Okay, so this is what we get then for the helical cone beam. You see the front and the bottom. The helical thing, you see a little wiggle going through all the layers. So this is for 64 processors, for 256 processors. And I can also show it in a movie where you see, so the first one will be circular cone beam. That's where the detector and the source, they rotate around the object, but they don't move in a vertical direction like the helical cone beam. That one we'll show afterwards. So this is the narrow, means that it is relatively far away. And you see that near the center, that the slabs are closer together. This is helical cone beam, so it's quite uniform how it's divided. The laminography, where both the source and detector move in a circle, and there you get these elongated blocks. And similarly for tomosynthesis, at the airport security, this is how you would split up the space. Okay, so the final method for tomography, which doesn't assign voxels, but is really only based on geometry, is the following. Here we have 4 processors. They all get a block, and then we look at what the shadows on the detector, what color they have. So if the color is only red, it means that the rays that hit that part, they only hit one processor. There's no communication. But you see there's the red and the yellow, and they overlap, we get orange. And that part is representing communication. So we want to keep the area of that area of shadows, overlapping shadows, as small as possible. So that is a projection-based method. It's purely geometric. Doesn't matter how many voxels you have. So with high resolutions, then the continuous is a very good approximation of the discrete, because in the end, we do have discrete computation. And if you want to know more details of this, Jan Willem Buurlager will give tomorrow a talk in the papers section of this conference. Okay, so this does work well. So we compared this to Astra, which is a state-of-the-art parallel tomographic reconstruction package. Astra only uses slabs, and it can only be used for the most simple geometry of the scanner, and that's the circular beam, the circular cone beam. In this method, so Astra employs GPUs, and it uses MPI for communication. So the dotted lines, they are Astra, and you see that, so for two different narrow and wide cone beams, that the wide one doesn't have any scalability, and the narrow one actually also not. Once you go beyond the 16 GPUs. But on the other hand, the new method, it's called Pleiades, the open star cluster. This method is employing this type of geometric partitioning, and also it is based on a library that was developed by Jan Willem Buurlage. It's called Bulk. It's based on C++ threads. You can use MPI as a backend for distributed memory, but you only need to write your code in a single system. So it's in a bulk synchronous parallel way, and that achieves speedups. Okay, so what does the reconstruction look like? This is thanks to Sofia Koban, who's a postdoc at CWI. She stitched together the picture of the art object. So if you look well, you can see that there's some resemblance. The reconstruction, of course, doesn't give colors. That's what we missed then, but that's what you see. So the conclusion. So we could solve 839 matrices to optimality using an exact solver, and I think we can do more. You can find them on the MondriaanOpt webpage, also the ones with the newer method. So to answer a question, how good is current partitioning? The answer is, for two processors, it's within 10% of optimal. Are we out of business as designers of parallel partitioning algorithms? The answer is no, because if you have, let's say, 256 processors, and you would lose 10% at every level of split, then you are still a factor of 2 from optimal, so there's something to be gained. And at the end, we showed a geometric method to find a good partitioning for scanners, also for very, very high resolutions. And that could solve extra large problems in a real production environment. I thank you for your attention.
So we have plenty of time for questions.
At the end, the airport setup seemed... Go to the microphone, please. Oh. So the airport setup, the solutions seem kind of regular with these slabs. Is there a way, at least for some of the problems, to come up with an analytic solution as opposed to a computed partition?
We've tried to use some analytic methods to solve the problem, for example, for the load balance. So it is a geometric, but they're very difficult integrals, and you can go from 3D, reduce it to a 2D problem, but you still will need numerics to solve that one. So we've tried, and that doesn't work. Yeah.
Work? No? Okay, let's speak here. So I have one question. Is you talked about optimal partitioning of the non-zeros of the matrix, but a lot of parallel codes actually use a 1D, like row slicing type of technique. So do you think it's worth the complexity of implementing, non-zero based distributions?
Okay, so the methods, you can use them also for the branch and bound methods, obviously also for one-dimensional solutions. The problem is if you have dense matrices, or matrices with relatively dense rows or columns, or both, then you will want to split in both directions. And because one dense row would cause an enormous load imbalance. And that's why in general, we would prefer 2D methods. But for the tomographic case, where we don't even have the matrix, let alone we cannot feed it for those big resolutions to a partitioner, then we need the simplicity of indeed a 1D method.
Last chance. Okay, no further questions?
Bora.
Oh, there is one more. Okay. Please go to the microphone.
So the optimality you defined is with respect to the communication volume?
Yes.
So would you be able to handle other metrics such as message latency and maximum volume per processor?
We didn't do that, but I think you can do it if you want to take number of messages also into account. It's the latency. Then you would have to fix a ratio between what does it cost to start up a message and what does it cost to send a data word. And if you fix the ratio at maybe 50, and I know that Jeffdet and Seer have written a paper on that, then you fixing that, you can also take that into account in a branch and bound algorithm, and that you could do that. Yeah.
Right, let's thank Rob again.